In the last video, we noticed that when you're on your closed interval from A to B, including A and including B, and you've got your continuous function, your absolute max or absolute min is located in one of two places. It's either where your local mins and local maxes are, or at your endpoints. Now, here's the thing. Finding the endpoints is not hard. You know where those are already. Your endpoints are just f of A and f of B, right? Just plug A into your function. That will tell you how high the function is. Plug B into your function. That will tell you how high the function is. In particular, plugging A into the function will tell you how high you are at the left endpoint, and plugging B into the function will say how high you are at the right endpoint. But the long story short is finding the function values at the endpoints is not hard because you know what your endpoints are. Here's the question. How do you find your local maxes and mins? Because if you could find your local maxes and mins, then you would know everywhere where your absolute maxes and absolute mins could be. So let's try to solve the riddle of, man, how do you find where the function hits a peak? How do you find where the function hits a valley? So question, how do you find the location of your local maxes and mins? Well, I'm going to answer this question not completely conclusively for now, but I'm going to answer the question by saying, well, they could only be in a couple places. So answer, they could only be, let's say only be where? And I'm going to fill in a couple cases. Okay, now to think about this. Imagine on your function you computed your derivative. Now you know from what we've studied previously that the derivative is the measure of the slope of the tangent line to the function. It's a measure of slope. Are you going uphill? Are you going downhill? Now, when you think about your derivative and you try to evaluate your derivative, because you know your derivative is itself just a function, you could plug x values in and get something out. What you get out of your function is going to be one of four things I claim. Your derivative could be positive. Your derivative could be negative. Your derivative could be zero, or your derivative could not exist. Those are the four possibilities, are they not? Because when you look at your derivative, you're either going uphill, downhill, neither, or you don't exist. Your derivative is a number. Numbers are either positive, negative, zero, or they don't exist. Well, what does a function look like whenever its first derivative is positive? When the first derivative is positive, the function is going uphill. And if the function's going uphill, think about this. When the function is going uphill, you couldn't possibly have a local max or a local min. If the function's going uphill, the function is increasing, it couldn't be a maximum because the maximum would have to be somewhere else to the right. It also couldn't be a minimum because the minimum is going to have to be somewhere off to the left. So, where the function has a positive slope couldn't possibly be the local max or min. No local max or min. Okay, what could the function look like if its first derivative is negative? What would the function look like if its first derivative is negative? First derivative, slope, slope, negative, downhill. So, if the function is downhill, like so, I claim you can't possibly have a local max or local min here because it couldn't possibly be a local min here because just go further to the right and you're farther downhill. You also couldn't possibly have a local maximum here because if you just go to the left, you're going to be higher. So no local max or min. So in other words, if we're trying to find where the local maxes and mins are, they can't possibly be where the derivative is positive or negative. Derivative positive, uphill, you're going higher to the right, lower to the left, can't be a max or min. First derivative negative, you're going downhill, lower to the right, higher to the left, could possibly be a max or min. What about these last two cases though? What is the function going to look like when the first derivative is 0? I claim one case of this would be like so. Right here at the peak, what is the value of the slope? The slope is not positive, the slope is not negative, the slope is between positive and negative. And what is between positive and negative? That is a slope of 0. And guess what? That could be a local max. And actually, if we flip this picture upside down to where you have a picture of the smiley face, I claim that point down there at the bottom has a slope of 0. Why? Because the slope is not downhill, the slope is not uphill, the slope is not negative, the slope is not positive. It's between the negatives and the positives, and the thing between the negatives and the positives is 0. So in fact, the slope is 0 at this max and at that min locally. So one place where you could find a local max or min is where your derivative is 0. That is one possibility. I claim it's not the only possibility, because think about what does the function look like when its derivative doesn't exist. What's the shape of that? Remember, derivative is a slope, right? What, f of x plus h minus f of x over h? It's a long time ago when we talked about that, but the long story short is derivative is a slope, or excuse me, derivative is a limit. And in order for a limit to exist, the slope has to be, in this case, the same from the left and the right. What if the slope weren't the same from the left and the right? You could have a function that was shaped like so. Here is a point where the derivative does not exist. Slope from left is different than slope from right. And this is a local minimum. And hell, if you flip the picture upside down, you could have a local maximum where the first derivative doesn't exist and you have a cusp. So, first derivative doesn't exist. That's another point where the function could hit a max or a min. Now, to be clear, let me be very clear. This is where they could be. I'm not saying you're always going to get a local max or a local min where the first derivative is 0. Take a look here. What if we had a function like so that sort of flattens out for an instant and then continues to ascend upwards? Because this function is coming in positively sloped, flattens out for an instant, but then goes out positively sloped. We haven't changed direction there, we haven't hit a peak, we haven't hit a valley. So this happens to be a point where the function has a horizontal 0 slope, but this is not a point where the function hits a max or min. So I'm not saying that everywhere the first derivative is 0, you have a max or min, but I'm saying if the first derivative is 0, it could be a max or a min. Similarly, if the first derivative doesn't exist, you could have a max or a min, but you don't have to. I mean, you could have a graph of a function that did something like this, and you could be increasing on the way in and increasing on the way out, and you never hit a maximum at that point. Well, so be it. That's okay. You don't have to hit a maximum when the first derivative doesn't exist, but you could. And here's something, though, we can say for sure. First derivative negative, you couldn't be a max or a min. First derivative positive, you couldn't be a max or min. So positive and negative slope values do not correspond to local maxes and mins, but 0 slope and no slope could. And that's a victory in and of itself. And in fact, these points where you could have a local max and a local min, we give language to that because these are special points. Where the first derivative is 0, where the first derivative doesn't exist, where you could have a local max or a min, these are called critical points or critical numbers. Why are they called critical numbers? They're called critical numbers because they are critical if you are going to understand the nature of a function as it ascends up or descends down, hits a peak, hits a valley. If you want to know where a function hits a peak or hits a valley, you need to look no further than where the first derivative is 0 or when the first derivative doesn't exist. The critical numbers tell the story there. And that makes them important. It makes them important enough for us to give a word to them, and a word as seemingly grand, I suppose, as critical numbers.